Hi, this video is immediately after the thermodynamics first law, the concept we're talking about. And so in essence, first law of thermo is delta E equals Q minus W, right? Okay, Q is heat, W is work. They both contribute the change of energy of the system. Let's look at some examples here today. So you have this container right here. There's a heat coming as 15 kilojoule. There's a heat coming out. And they ask what's the energy change of the system. Obviously, there's no work done to the system or work done by the system. So work is 0. So that situation, this example, we call this example 1. My example 1 will be my delta E is equal to, there's a Q, there's a heat coming, remember, and there's also heat coming out. And so heat coming is going to be 15 kilojoule positive based on the sign convention we're talking about. If there's a heat coming, it's positive. If there's a heat coming out, that's going to be negative. So that 3 is going to be negative 3. Then that's together going to give us 12 kilojoule. Since there's no work here is 0. Okay. So that's delta E energy change for the first system. Pretty straightforward. Now let's look at example 2. So for this system, there's electrical wire, like a resistor here, that is in this adiabatic. All right, what does adiabatic mean? Adiabatic mean we're talking about in the type of process video, that means Q equal to 0. There's no heat transfer. However, there's electrical work down to the system because there's a wire, have electricity going through. So there's electrical work down. But we still start with the same governing equation, which is delta E equal to Q minus W. For this situation, our Q is equal to 0 because it is adiabatic. So we just have minus W. Now we have to remind ourselves about the correct sign convention for W. Okay? So work down by the system is positive. Work down to the system is negative. So you tell me, how about this one? Is this work down to the system or work down by the system? Of course, it's work down, electrical work down to the system. So that's going to be negative value. So we have minus, and this W will be negative value, and it's 5 kilojoule. So it's a minus negative value, then we have increase of energy of 5 kilojoule. Okay, so that's for that example. Now let's look at example 3. So there's a fan here, and that's connected to this shaft. And again, this is adiabatic system, which means Q equal to 0. And we are going to start with our same governing equation. So the equation will be delta E equals Q minus W. Since it's adiabatic, for this situation, Q is equal to 0, so 0 minus W. And again, use sign convention for work. This is work down to the system, right? Because the shaft is turning the fan, and so it's down to the system. If it's down to the system, so it's going to be, this W would be negative value. So you have minus a negative 8 kilojoule. Then that's going to give us 8 kilojoule. Okay, so that's the increase of energy of the system for that situation. All right, let's continue looking at something more. Well, this has nothing new. The energy change is, for this situation, you have a work down to the system. Then let's call this example 4. So we start with delta E equal to Q minus W. Again, this is adiabatic, so Q is equal to 0. So it's going to be negative W. And this is work down to the system. If it's work down to the system, it's negative value, negative 10. So we have increase of energy of 10 kilojoule. Okay. And this is another example. We call this example 5. In this example 5, start with the same governing equation, delta E equal to Q minus W. And however, this is not adiabatic. And there's a heat coming in, that's positive, based on sign convention. There's a heat coming out, so that's negative, based on sign convention. And there's a work done to the system, so that's going to be W to be negative 6. So all those together, 12 plus 6, then we're going to get 18 kilojoule. Okay. All right, another example. So we have this one here. Again, for every single, we call this example 6. We always start with delta E equal to Q minus W, our first law of thermodynamics. And here, it is assumed it's stationary, which means delta KE and delta PE, kinetic potential energy change is 0. So because of that, we can just, because delta E we're talking about in the previous video is delta KE, delta PE, and also delta U. In this situation, will be just delta U now. So the heat and the work here contribute the internal energy change, delta U only. Then delta means change is always final minus initial, U2 minus U1. U2 means the final state internal energy, U1 its initial state internal energy. And Q, is there any heat coming into the system? No, so that's 0. However, there's a heat leaking out, so that's going to be negative 500 kilojoule based on sign convention. And then minus this W. There's no work done by the system. However, there's work done to the system. There's a shaft and turning the fan down to the system, and that's going to be negative 100 kilojoule because work done to the system is negative. Okay, so in that situation, we'll calculate that. So negative 500 plus 100, so we get negative 400 kilojoule. Then they want you to find what's the final internal energy, U2. Then we have U2, initial internal energy is 800, substitute in is equal to negative 400. Then we can find our U2. That will be equal to 400 kilojoule. Okay, so that's another example of first law. Now let's look at final example. We call this example number 7. For this example, here what they say is, okay, if I plug this fan and I have power input, realize here is the power in watt, so that's a power. With 20 watts of power, they said this fan is going to turning of 1 kilogram per second. That's mass flow rate, and of 8 meters per second of speed. And here you are going to judge it. You are going to evaluate it. See if this is claim it is feasible, right? If it holds true. So you're going to use first law, basically the conservation of energy, to figure out if it's true. How do we figure it out? We start with the same equation, delta E equals to Q minus W. All right, let's think about this. So this situation, consider it's ideal situation. There's no heat transfer, right? So Q here, we assume Q is equal to 0. And they also consider there is no potential energy change, and there's no internal energy change. The only thing that's changing is the speed of the fan, right? It's the kinetic energy change. So in that situation, for this particular scenario, my delta E will only have delta KE. And there's no Q, no heat transfer, will be just work. Okay, so we're making an assumption for this. So we give them the most benefit of doubt, right? Consider all of this work down to the system is completely to increase the fan speed. There's no friction, nothing, right? We give them the most maximum speed they could get, So in that situation, let's think about it. However, this work here is not in energy form, it's in watt. We know energy divided by time give us power, it's in watt. So here we're actually going to divide it by time. Why not? Right? You can. Because this is going to happen a lot in the future. When you have energy divided by time and this work divided by time, then you're going to get joule per second. Joule per second is going to be, for this, is going to be 20 watt. Okay. And now let's think about kinetic energy. Kinetic energy normally is what? Half mv squared. That's in joule, right? That's in unit, is in joule. If you're going to change joule to watt, again, we're going to divide it by time. So if we're going to divide it by time, this delta K divided by time, let's take a look at it. What is half mv squared divided by time? Now, what's mass over time? That is going to be our mass flow rate. We're talking about m dot in the some videos in engineering fundamental. Is half m dot v squared. That's equal to 20 watt, right? That's it. And we don't need to know the mass, we just need to know the mass flow rate, which means how many kilogram flow per second, which we do know it's half. So if this is conserved, if all of them is conserved, what is the maximum speed you can get? That's what we're trying to find. If this is a situation, what is my maximum flow speed can potentially get? Right? So in that situation, I'm going to use 20 times 2. So I'm trying to solve this V. So 40 divided by mass flow rate and take a square root. And let's take a look. 40 divided by my mass flow rate, which is 1 kilogram per second, then will be just square root of 40. And what is square root of 40? We'll have 6.32, and that's velocity. That's going to be meter per second. And then we compare this number with this 8 meter per second. So maximum speed you could get 6.32, and this person claim it's going to speed up to 8 meter per second. Is that possible? No. So this claim is not valid. And in order to do that, you figure out using the first law of thermodynamics to make this evaluation. All right, hopefully I had fun through those examples of first law of thermo. I'll see you next time. Bye.